Hello everyone, James from JTS Maths Tutoring here. Today we are continuing with our example of graphs and functions. We are continuing with the very same example that we used the last time. The only difference is that when it comes to determining of horizontal and vertical asymptotes, today we are going to make use of limits. So let's get started. First question, determine the y-intercept. We all know that the y-intercept, this is where the graph crosses the y-axis, and at that point, the x-coordinate is equal to 0. So we plug in the value 0 for x into the original equation. You can see here I've rewritten this as a rational function. So you plug in 0 for x there, you get a 0 there. E to the power 0 is going to be a 1. So 0 over 1 is going to be 0. Therefore, the x in the y-intercept is equals to 0, 0. Determine the horizontal and vertical asymptotes. Right. So a function is said to have a horizontal asymptote at y is equals to b if the limit of the function f of x as x approaches infinity is equals to b, or if the limit of f of x as x approaches negative infinity is equals to b, and your b is infinity. So let's get started. So what is the limit of f of x here as x approaches infinity? You can see here that we have got an indeterminate form of the form infinity over infinity. Therefore, we apply our L'Hopital's rule. We get the derivative of the numerator and the denominator on its own. So here you are not applying the quotient rule here. Take note of that. So derivative of x is going to be 1. Derivative of e to the power x is going to be e to the power of x. Then now you substitute your value for x there. You're going to have 1 over infinity, which is going to be equal to 0. And you do the same for when the limit is approaching negative infinity. You still get your infinity over infinity, which is an indeterminate form. You apply your L'Hopital's rule. You get a 1 over e to the power of x, which is going to be equal to 1 over 0. And the final result is going to be negative infinity. But remember that your b has to be infinity. Therefore, this function has got a horizontal asymptote at the line y is equals to 0. All right. What about the vertical asymptote? A function of f, or a function f, is said to have a vertical asymptote at x if the limit of f of x as x is approaching a particular real number is equals to infinity, or if it is approaching a particular real number, it's going to be negative infinity. So you can see that here my c is any particular number or point where the denominator is going to be equal to 0, or the function is what? Undefined. Not the limits to be determined here. It can either be a one-sided or a two-sided. So looking at this question, you can see now that the denominator of the given function, it can neither be negative nor 0. And also the function does not have any undefined points. Hence, f does not have a vertical what? Asymptote. All right. So our c and d here, we need to use the sign pattern for the first derivative to determine the intervals over which f rises and where it falls, and also to get our local extrema. And also we need to make use of the sign pattern of the second derivative to determine where the graph is concave up and where the graph is concave down, as well as locate the point of inflection if ever we have one. All right, let's get started here. So the first thing that we need to do is to get our first derivative. So you can see here, I left it as it is. I did not rewrite it as a rational function. So I'm going to make use of my product rule here. So you first get the derivative of x, you multiply it by the function e to the power minus x. Then you add the derivative of the second function multiplied by the first function. So what is the derivative of x? It's going to be 1 multiplied by e to the power minus x. You get your e to the power minus x here. The next one is that you get the derivative of e to the power minus x, which is minus e to the power minus x. So that's why you see that my positive sign fall away here. All right, then you multiply it by the first function, which is x. So you are here. Now I factor out e to the power minus x, then I have 1 minus x, or I can rewrite it like this. All right, there's a reason why I decided to rewrite it as a rational function here. So whilst you are still at the first derivative, let us quickly go to the second derivative. With the second derivative, I'm actually going to make use of the quotient rule. So with the quotient rule, you get the derivative of your numerator, you multiply it by this function here in the denominator. Then you subtract the derivative of this denominator, you multiply it by this function in the numerator here, all that over, you square your denominator. All right, let's get started. So what is the derivative of 1 minus x? You're gonna get minus 1. You multiply it by e to the power x, you get your minus e to the power x here. You subtract. What is the derivative of e to the power x? It's going to be e to the power x, and you multiply it by this function here in the numerator, which is 1 minus x. Then you square your denominator, which is going to be e to the power x squared, to give you e to the power 2x. Right now, you have to simplify what you have right here. So you're going to have minus e to the power x minus e to the power x plus x e to the power x. So you now have minus 2 to the power x plus x multiplied by e to the power x, all that over e to the power 2x. So if you factor out your e to the power x here, you're going to have e to the power x, and in brackets x minus 2, all that over. So you can cancel these factors here, so you'll be left with this. So, okay, that is our second derivative. Right. So now when it comes to our sign pattern, so we'll start with the sign pattern for the first derivative. All right. So we are here. So you need to get what are called critical points. What are critical points? These are simply points where the function is defined and its derivative is 0 or it is undefined, of which from here you can see that the only critical point that we are going to have here is 1. Because if you plug in 1 there, 0, yeah, you're going to get your 0 there. Okay, cool. Right, so since we only have got one critical point, so that one critical point is actually going to split our number line into 2 distinct intervals. If, for instance, I've got 2 critical points, they will split the number line into 3 distinct intervals and so forth. All right, cool. So let us look here. So we have got 1, which is our critical point. So we have got numbers on the left side of 1, and we have got numbers on the right side of 1. Okay, cool. Right. So what we are going to do here is that we plug in this part of the function here and the entire function here. All right, cool. So how do I know that this is going to be positive, this is going to be negative? I simply look at this part of the interval and I look for any number which falls within this interval. Say, for instance, let me get here minus 1. If I plug in minus 1 here, what do I get? It's going to be 1 minus 1, which is going to be 1 plus 1, which is going to give me a number which is what? Which is positive. So what's going to happen to this entire function here is that when you plug in minus 1, you're going to have a positive, right? Okay. You come to this side here, any number that is within this interval. For instance, let me take 2. If I say 1 minus 2, what do I get? I get minus 1, which is a negative number, right? So you notice that when you plug in minus 2 here, this entire function is going to be negative. So you've got your negative here. All right. So now look at this. F rises where there are positive signs on the sign table. F falls where there are negative signs on the sign table. So where do we have positive signs? It's right here within this interval here. So we actually say F rises right here within this interval, and it falls within this interval here. All right. What about local extrema? So local extrema occurs where the first derivative changes the sign on the sign table. So here we can see we are changing from positive to negative here. So we have a local maximum here. But if we were coming from a negative to a positive, it was going to be a local what? Minimum. So we have a local maximum here at F is equals to 1. So what we do here to get the y coordinate, we do not plug in this one into this derivative here. You plug it into the original function. So there is a local maximum, it's 1, 1 over e. All right. So for us now to know where the graph concaves up or concaves down, we make use of the sign table. We make use of the sign table of the second derivative. Right. So we do exactly what we did here. Right. So I've got here x minus 2. I'm looking at what is my critical point. Okay, the critical point there is going to be 2. So I look at this interval, I get any number here, say minus 5. If I plug in minus 5 here, I'm going to get a negative sign here, of which the final result of the entire function is also going to be what? A negative. Let me look at this interval here. Any number. So let me say take 10 there. 10 minus 2 is going to be 8, which is positive. Right, which means at the end of the day, whatever I'm going to get here, if I plug in 10, I'm going to get a positive here. All right, cool. So let's look at where does it concave up and where does it concave down. F is concave up where there are positive signs on the sign table, and F is concave down where there are negative signs on the sign table. Right, so where do we have positive signs on the sign table? It is within this interval. And where do we have negative signs on the sign table? It is within this interval. So we say F is concave up in this interval here, and F is concave down in this interval. Right. How do we get a point of inflection? That is if ever we have one. An inflection point is a point on the graph at which the second derivative changes the sign. This is where concavity changes. So we can see here it changed from being concave down to concave up at 2. Like what we did here, we do not plug these 2 into the second derivative, but into the original what? Function. So at the end of the day, we have our point of inflection at 2, 1 over e to the power 2. There we are. Yes, sir. We actually done answering this question. So if you have any queries or you have any suggestions, please feel free to write to us on our Google My Business site, our Facebook page, as well as our Instagram page. But at this point in time, allow me to do what my mama taught me. A good visitor knows when to leave, or she would say, a good dancer knows when to leave the dance floor. Adios, amigo.